Hi. Hi, good morning. I'm Li Chen from Zhongguancun Laboratory, and today we are going to have 4 exciting papers. Let's go on to the first one. It's PPT. The presenter is Shuo Lide. Lide is currently a first-year PhD student at the Tank Lab of Tianjin University, under the supervision of Professor Wenxin Li. His primary research interests include data center networks, transport control, and RDMA networks. And please.
Thank you. Thank you for Lich's instruction. Good morning, everyone. My name is Li Desuo from Tianjin University. This work, PPT, a pragmatic transport for data centers, is a joint work with Yiren Pang, Ren Jiepei, Professor Ke Qiu Li, Professor Xiulong Liu, Xin He, Professor Yitao Hu from Tianjin University, and Professor Wenxin Li from Tianjin University and Huaxia Haorui Technology Company Limited, and Professor Guyue Liu from Peking University. In recent years, as shown in the figure, the link speed of production data centers grows fast from 1 gigabits to 10 gigabits and to 200 gigabits and now reaching 400 gigabits and beyond. So this trend made the networks with higher BDP, shorter FCT, and more flow burst. This requires transport to provide higher throughput and lower latency. Existing solutions can be divided in 2 lines of work. The first line of work is reactive transport, which starts from a small initial window and iteratively ramp up to the right rate. Most of reactive transport are good deployable, but they fall short in utilizing spare bandwidth or optimizing FCTs. Another line of work is proactive transport, which proactively allocates the bottleneck link bandwidth. The proactive transport may achieve good performance, but they require significant, but they are challenging to deploy because they require significant modification to TCP/IP layers or assume a prior knowledge of flow size. In this work, we aim to explore a new transporter that can achieve good performance while being readily deployable. We ask, is it possible to leverage reactive transport's both deployment advantages and address their performance issues? There are 3 key insights in our work. The first one is DC-TCP is a good start. So as shown in the table, DC-TCP has been widely adopted in industry and has been integrated with various OS kernels. Furthermore, it requires no switch modification and it is application friendly. The second key insight is we think the key culprit is underutilization. When multiple flows share a bottleneck bandwidth, the spare bandwidth will emerge in 2 cases. The first case is in the slow start phase. The spare bandwidth will emerge in the first multiple RTT for each flow as it needs to convert to the ideal window. Another case is in the queue build-up phase, the spare bandwidth will emerge when multiple flows are marked with ECN so that they will cut their window simultaneously. To show this point, we run a macro simulation and generate traffic under 50% network loads. As shown in the figure, the link bandwidth achieved by DC-TCP between 25% and 50% at most of time, and there are 50% spare bandwidth at special time. So thirdly, we think filling the gap to maximum window is good. We have constructed a hypothetical DC-TCP which sends opportunistic packet to fill the gap to maximum window of each flow. And we run simulations and find that the hypothetical DC-TCP reduces the overall average FCT by 33% and 40% compared to the HOMA and NDP respectively. Moreover, we compare the performance under different window sizes, and we find that filling the gap to maximum window achieves the best performance. Oh, sorry, it's this PPT. Sorry. we put it all together, we design the PPT. To utilizing the spare bandwidth gracefully, we designed a dual loop rate control which has a high property control loop and a low property control loop. The high property control loop following the behavior of DC-TCP and send a normal packet using DC-TCP's congestion control algorithm. And the low property control loop combines two technicals. An intermittent loop initialization and an exponential window decrease to send the opportunist packet to gracefully utilize the spare bandwidth left by the high property control loop. The first technical of PPT is of the low property control loop is the intermittent loop initialization. Because of the window dynamic nature in DC-TCP, the spare bandwidth left by HCP appears intermittently. So whenever it appears, PPT will open a low property control loop and calculate an initial window for opportunistic packet transmission. Specifically, for the slow start phase, the PPT will set in the initial window to the BDP minus the window size of HCP, and for the slow start, for the queue build-up phase, PPT will set in the initial window to 1/2 minus the minimal value of alpha and times the maximum window size. Another technical of low property control loop is the exponential window decrease, which ensures in every single RTT the summation of HCP's high property control loops window size and the low property controls window size will not exist the maximum window. Specifically, the receiver will send one ACK for every 2 data packet it received, and the sender will send one new LCP data packet for every LCP ACK it received. So the sending rate of opportunistic packet is naturally cut by half after every single RTT. Okay. When packets are marked by ECN because of the link congestion, the PPT will ignore all ECN marked ACK to quickly reduce the LCP's sending rate to avoid harming the HCP's the high property control loop's performance. As shown in the figure, by combining above two technicals, PPT can gracefully utilize the spare bandwidth left by the DC-TCP. Despite being effective, the dual loop rate control treats the small flow and large flow equally in the network. So as shown in the middle example in the figure, the packet of small flow will be queued after those of large ones. So this results in the extra latency for small flows packets. So we think the flow scheduling is must, but we still face two challenges. The first challenge is how to differentiate the large flow from small flow without unknown flow size in prior. To meet the challenge one, we proposed the buffer-aware flow identification. When user data is copied to the socket sender buffer through the system call, we will calculate the first data copy's size and compare it with the flow identification threshold to classify whether either is a non-large flow or a large flow. The efficiency of the buffer-aware flow identification has been demonstrated on both memory cache and web search real-world application, with accuracy rate reaching 86% and 84% respectively. The second challenge is how to prioritize the small flows with penalizing overall performance or starving large flows. For challenge 2, we designed the Mary symmetric packet targeting. It aims to assign higher prioritize for flows with the fewer bytes while ensuring the HCP traffic, high property control loops traffic is not impacted by the low property control loops traffic. PPT lets its high property control loops packet use the first 4 high prioritized while the low property control loops packet using the remaining 4 low prioritize. So if a flow is identified as a large flow, it can only use the lowest priority in corresponding priority range, and in contrast, if a flow is identified as a non-large flow, it can use the other prioritize. The high property control loop send data from the beginning of the socket send buffer, while the the low property control loop send data from the last byte of the socket send buffer. In this example, the packet 1 sent by the high property control loop is marked with the priority 3, which is the lowest priority in high property control loops priority range, and the packet 8 sent by the low property control loop is marked with the priority 7, so it's the lowest priority in low property control loops priority range. For flow 2, which is identified as a non-large flow, the packet 1 and the packet 6 is marked with the highest priority in corresponding priority range. Since flow 1 is identified as a large flow, it will transmit its all packets with the same priority. And in contrast, for flow 2, as more bytes are sent, the HCP, the high property control loop and the low property control loops packet prioritized will be demoted at the same pace. The priority of flow 2 demoted until it reaches the second lowest priority in corresponding priority range. So by combining about 2 techniques, we propose the buffer-aware flow scheduling. Looking back at this example, in the first step, the ball flow is identified as a non-large flow, and the below flow is identified as a large flow by buffer-aware flow identification. And in the second step, the packet is marked with different prioritized by Mary symmetric packet targeting. At this point, the packet in the switch buffer will reach the same order as the ideal. In summary, through buffer-aware flow scheduling, PPT reduces the extra latency for small flows and ensures the high-property control loops traffic will be not impacted by the low-property control loop. We have implemented the PPT's prototype as an extension to Linux kernel with about 400 lines of code. At the switch side, we only need to configure the ECM marking and the strict priority queuing, which is an in-building function in existing commodity switches. We implement PPT control logic and flow scheduling as the Linux kernel within the TCP and IP layers. Now we came to the testbed experiment. We used to widely adopt realistic data centers workload, web search, and data mining. We construct auto traffic pattern and in-cast traffic pattern to evaluate our PPT. We compared PPT with Homa Linux RC3 and DCTCP in testbed experiment. We found that PPT reduced the overall average at FCT at least 79%, and PPT reduced the small flows per average FCT at least 84%. We further show the performance under in-cast traffic pattern. For overall and large flows performance, PPT achieved the best, achieve up to 95.5% and 95.1% performance improvement respectively, and PPT reduced the small flows average and tail FCT at least 72% and 88%. To show whether PPT will incur high CPU overhead, we measure the kernel space CPU overhead of PPT and DCTCP in our testbed under web search workload. Figure shows that the largest gap between their CPU usage is less than 1%. We also did simulations based on the NS3 simulator. We again used a tool workload, and we compared PPT with both reactive transport and proactive transport. For overall and large flows performance, PPT reduced the overall average FCT by up to 87%, and PPT reduced the large average FCT by up to 90%. And for the small flows performance, PPT achieved the best small flow performance under web search workload, and the gap between PPT and Homa's average and tail performance under data mining workload is 6.3% and 54%. In summary, PPT is a pragmatic transport with two components. Firstly, PPT employs a dual loop rate control to gracefully utilize the spare bandwidth to optimize FCTs, and it also has a buffer-aware flow scheduling to scheduling flow without prior knowledge of flow size and without affecting the benefits of dual loop rate control. That's all. Thank you.
Two very small questions. One is, you said you ignore ECN for the low priority flow that is on its way down in using the spare bandwidth. Why do you ignore ECN?
No. Sorry, it's a good question, but we not ignore the ECN in low probability control loop. In contrast,
you should try to reduce faster.
If the LCP packet is marked with ECN, we will reduce the LCP's transmit rate more than the high probability control loops are marked with ECN.
Good. The other question is, maybe I didn't understand.
Okay.
You take all the packets of a flow and you put them in different priorities, right? And does that result in a lot of packet reordering that you have to fix? No?
No, I think we. Maybe I can't. I have not understand the question.
I can ask you offline.
Okay, thank you.
Okay, great work. I have a question. Considering that RDMA is widely used in data center, so does your design work in RDMA NIC?
No, we implement the PPT in the Linux kernel. So as we say that the LCP, the low priority control loop send the data from the last bytes of the socket send buffer. So the disorder in RDMA will occur high performance demoted. So we just for the TCP based solutions.